So let me begin. I'm David Spergel. I'm a director here at the Center for Computational Astrophysics and want to begin by welcoming you to the Flatiron Institute and to the Big Apple Magnetic Field Conference. And I thought I'd just say a few words about the Flatiron Institute and the Simons Foundation for those of you who this is your first time here. So the Simons Foundation is funded by Jim and Marilyn Simons. Jim Simons is a topologist. He's the Simons of Chern-Simons number. That turned out to be a very profitable topology. That plus hedge funds made him a very wealthy man. And he and Marilyn have given more than half their money to set up a foundation to support, among other things, basic research in science. And the Simons Foundation, for a number of years now, has been funding external grants, and people may be familiar with Simons investigator programs and collaborations. And about 5 years ago, Jim and Marilyn convened a meeting as they wanted to expand the reach of the foundation and looked for suggestions on what to do. And Ingrid Delbechet convinced them it would be a good idea to build a center focused on computational science. Ingrid's vision probably involved having it at Duke, but Jim wanted it across the street from the foundation. So we got this building, and over the past 3 years have remodeled it. We're just in the very final stages of remodeling the building. And then Jim started to bring people here to run the centers. The first center set up here was the Center for Computational Biology, which is directed by Leslie Greengard. Then I was brought here to run the Center for Computational Astrophysics. We've set up last year a Center for Quantum Materials run by Antoine Georges and Andy Millis. We just set up this fall a Center for Computational Mathematics. Leslie Greengard moved from biology to math, which was his true home. So we're actually now looking for a Center for Computational Biology. I'm on the search committee, have good names, let me know. And we're thinking about potentially setting up a Center for Computational Neuroscience as a fifth center across the street. And we have a 35-year lease on this building, and the plans are basically to operate the center for the long term. So right now, the CCA, the broad mission is to support computational astrophysics. Roughly speaking, we have about half our people here working on how do you get from initial conditions forward, simulating the universe, and about half the people working on how do we get from data to understanding, doing big data work. And of course, we hope that these two things interact as often as possible. We've got 7 research groups, or 6 right now, 7's going to start soon, on galaxy formation, astronomical data, compact objects, gravitational waves, cosmology and data science, planet formation and dynamics. A lot of the people who are group leaders, 2 of them, Rachel and Shirley, are full-time here. The rest hold joint positions, as do I, with surrounding universities. So we have joint appointments at both the senior level and the junior level with Stony Brook, NYU, Columbia, Rutgers, Museum of Natural History, Princeton, and University of Pennsylvania. We also have a job advertised with the University of Connecticut. So Blakesley, who's one of the key people responsible for making this work, is full-time here this year, but next year will be joint as an assistant professor with Rutgers. And that's one of the models we have for building up the staff. So we've got this mix of these cross-appointed research staff. We're trying to be pretty strongly connected to the surrounding universities. We also have some full-time people here in research staff positions, but most of the people here will turn over on various timescales. So we've got about 25 postdocs, a large sabbatical visitor program until about 6 to 8 sabbatical visitors, and lots of short-term visitors here on scales of a day to a month. And one of the things we're nicely set up to do, and I hope this meeting will be a successful example of, is run workshops and meetings. So we ran, and sometimes these things are small, 6 people in a collaboration getting together here. Sometimes it's a meeting that fills this room. But I think we ran 40 meetings last year. So there's just a lot of activity. And, if, for some of you, I know this is your first time here. I hope you have you come and visit us often. And we really do feel one of the ways we gain a lot and contribute is being a place that can draw people together. Just say a few words about the space, so hope we have some time to wander around. So we have the whole building is ours. This floor is for meetings. Floors 3 through 10 are the different centers. 3 and 4 is computational mathematics. 5 and 6 is computational astrophysics. So there's a lot of us up there. So I hope some of you during the breaks will come up to 5 and 6 and say hello and see your spaces there. 7 and 8 is biology. 9 and 10 quantum materials. The 11th floor is our dining hall, which we have a constant flow of coffee, fancy coffee machines, cold brew, iced tea. You should note there's really good cold brew on tap, on the taps outside. You may not, no one has used it yet. You start to feel any jet lag. I know some people came in from Europe. One tall glass of cold brew will sustain you for a long time. But do come up to the 11th floor. The 12th floor, we have a roof garden. It's not officially open. Though at the director's meeting, I asked Jim Simons yesterday, I said, when's the roof opening? And he said, oh, just ignore the sign that it's closed. So we have it from the highest authority. We can probably stick our head out and wander out in the roof garden. But that is a fun space to go. This looks like a terrific program. I'm hoping to be here for as much as possible and really excited to learn. So thank you all for coming. Thanks to the organizers for putting together a great program, and this should be fun. Thanks.
I'm all set.
Oh, you're set.
Okay, so I should also mention a few things about our program. So you can find printed copies of the program outside. You can also go online to the website. The program is updated continuously. If there's any changes, you can find it there. We're also live streaming. So if you have any colleagues or students that wanted to be here but couldn't make it, you can direct them again to the website and they can check out the live streaming. And we'll also take questions from the live streaming via the chat in the live streaming. So hopefully we will get a few questions from our streaming audience as well. All right, so I am going to kick off the first session, which is primarily about star formation, shocks, and magnetic reconnection, talking about early phases of star formation, what sets the star formation efficiencies, and the initial critical density conditions for how stars form. So when thinking about this problem of star formation efficiencies and what are the initial conditions, namely the critical density for star formation, I'm really talking about what I consider and what many consider sort of a bottom-up analytic model for how stars form. Bottom-up here meaning from the sort of tens of parsec scales of GMCs down to protoplanetary disks. And a very common way of approaching this is to say, well, there's turbulence, there's magnetic fields in these giant molecular clouds, and those essentially have a lot to do with regulating both the efficiencies as well as sort of critical conditions for when collapse starts to take place. So we can't ignore turbulence, we can't ignore magnetic fields, and of course, the formation of the stars themselves then feed back on the turbulent magnetic fields via feedback processes. So the two things I want to address in this very short talk are, one, why is star formation inefficient? And of course, I basically already gave you the answer. It has something to do with feedback, turbulence, and magnetic fields. But how can we put that into an analytic framework? And then also, how do we calculate, or how do we measure observationally or analytically or numerically a density threshold for star formation? Or does a density threshold even exist? Is that even an interesting question? And I will, of course, address how this depends on magnetic support. So and another way to say that pictorially, the inefficiency of star formation. This is, I think, one of the key problems of star formation. Why is star formation inefficient? So stars, converting gas into stars occurs at about a 1% efficiency. And this is really amazing because we see it across all redshifts in various different galactic environments, including in local GMCs. So we have about this 1% efficiency of converting gas into stars. So this is a plot from a paper by Mark, which summarizes a lot of different observations at a wide range of redshifts, plotting the star formation gas surface density and the gas surface density divided by the characteristic freefall time. And then this line here is showing you that this conversion of gas to stars is about at 1%. This is important for cosmological simulations, of course, which a lot of times they don't resolve the necessary scales for star formation, and so they basically put in this 1% by hand. The other thing that I will talk about, of course, is this density threshold for collapse. We have a number of ways of tracing this, so I put up a few statistical ones that I think we'll hear about more throughout the week or throughout these couple days. The PDFs, which I'll address here, the density PDFs or column density PDFs, the relative orientation of the magnetic field and the density, and also the relationship between the measured magnetic field from Zeeman observations and the column density or density. So all three of these different statistics show this shift between diffuse turbulent gas and collapsing dense molecular gas, which the dynamics begin to be dominated by gravity. And both of these points, the inefficiency of star formation as well as the critical density, actually can be encapsulated analytically in a very simple way. And a popular way of doing this is to consider the density PDF or density distribution of gas in a turbulent magnetized molecular cloud. And there's a number of different analytic models that use the density PDF of a turbulent medium to do all sorts of interesting things like calculate the initial mass function, calculate the star formation efficiencies, the critical density, or even galactic relations like the Kennicutt-Schmidt relation. And this is simple because essentially you know that turbulence sets this log normal density distribution, and then you say, well, past some critical density for star formation, whatever that may be, all of this gas is now available to form stars. And so if we just integrate over this log normal density distribution, multiply it by a characteristic timescale, so usually the free fall time, which is also a function of density, then we can calculate a star formation rate per free fall time or a star formation efficiency. So this is a really simple and elegant way of relating a model for star formation to all of these interesting quantities which we'd like to understand. And the log normal probability distribution function of turbulence has another interesting feature, which is that it becomes wider, or the variance increases as you increase the Mach number. And so I'm showing you here a Mach 0.5 numerical simulation of turbulence, which is subsonic. There's not strong density fluctuations, and so you can see that the corresponding PDF is quite narrow. And as I increase the Mach number, you get strong density fluctuations because of the shocks. The PDF becomes wider and wider. And you can see that if there was some critical density for star formation, your PDF would become sufficiently broad to push some of that density over the critical density for star formation. And then you would have stars forming. And so this is one reason why a lot of these log normal models for star formation depend in some sense strongly on the strength of the turbulence or the sonic Mach number. This is a really nice review by Federath and Klesson, 2012, where they review a number of these log normal turbulence models and show how they depend on things like the sonic Mach number of the turbulence, the virial parameter of the cloud, and you can see here that the Mach number in some cases is a very strong parameter for setting the star formation rates or star formation efficiencies. Here's a number of other sort of log normal models that are listed here in their paper, and then they also have this nice table listing the critical densities, right? So the density threshold at which you need to overcome to start forming stars. So essentially, the predictions and features here are that you should get higher star formation efficiency with increased amount of turbulence. The star formation efficiency should stay constant if the turbulence properties stay constant. It's another feature. And then this critical density for the star formation, which is very important, essentially is set by the post-shock density. So the density that scales like Mach number squared if it's isothermal turbulence. And of course, the virial parameter is also important. So those are the basic features. How do the observations stack up to those predictions? Well, I could talk at length about this, but I'll just show one example of where we think these theories need to be modified, and that's when you consider the star formation rate and the Mach number relation. There really isn't a strong correlation observed, at least in local giant molecular clouds. And here, this is data from Kainulainen and Federath, 2014, a number of different molecular clouds where the Mach number is measured from CO line widths, and the star formation rates are measured from YSO counts. And that's about as good as you can do for these sorts of observations, and you don't really see any sort of clear trend between these two. The other, I think, challenge for these kind of models that use log normal PDFs is that essentially you have to plug in the efficiency by hand. And the reason for that is there's no feedback that's put into these models if you just consider a log normal density distribution set by the turbulence. So there has to be some additional way of including feedback. And so you just stick in a number that fits the data, which is fine, but it's still a little unsatisfying if we want to try to explain from first principles things like the Kennicutt-Schmidt scaling. So what can we do? Is there any hope for these models? And I think there is. And this is, I think, a critical modification that needs to be made. And that's actually the density distribution in molecular clouds is not necessarily a log normal. And in fact, there's a lot of papers, mostly recent papers, that have been coming out observational and numerical that suggest that the PDF of the density or column density distribution is actually a log normal in the low density gas or the diffuse gas, and then it becomes a power law at very high densities, right? Especially when you have active star formation and gravitational collapse occurring in the medium. So this allows us to modify a lot of these log normal only models, and now instead of just a log normal, we consider a piecewise function where we have this log normal plus a power law model. And essentially the mechanics of this are the same. We can just, instead of having a log normal, now we have also a power law. The power law slope can vary as a function of time, so it becomes shallower or steeper depending on the interaction of gravity, turbulence, feedback, and magnetic fields. And if you assume that this PDF is differentiable and continuous, then you can easily solve for the transition point, the transition density at which the log normal and power law transition, as well as the amplitude. So this is sort of how this looks like. You still have the width set by the properties of turbulence, but now you have this power law slope, essentially, which is governed by the evolution of star formation. And of course, you have a critical density still, past which this power law can start to form. However, an interesting feature of this sort of approach is that as the cloud becomes more actively star forming, the transition density moves up the PDF and starts to roughly approach the critical density. This allows you to extremely simplify your calculation for the integrated efficiency of star formation, especially in actively star forming clouds, because you can just say, well, the transition between this diffuse supported gas and the self-gravitating gas is just the ratio, or this dense gas fraction, of the power law portion to the total gas. So this essentially is the integrated efficiency, and you can even say, well, imagine that feedback regulates this slope, right? So as stars form, they kick gas out of this power law portion, then essentially you can remove any sort of fudge factors that are involved in this calculation and see how well does that match a numerical simulation where you can directly calculate the star formation feedback, or observations where you can directly measure the star formation rate from YSOs. So that's essentially what we've done with Uni Kainulainen, where we can directly measure the star formation rate in local GMCs from YSO counts and compare that to what this analytic model would predict by plugging in things like the Mach number of the cloud, the mean density, the cloud mass, and the measured power loss slope of the PDF. Since they're local clouds, we can actually resolve the PDF slope. And so we do fairly well in terms of predicting the star formation rates, the error bars here, because we don't necessarily know if the turbulence is solenoidal or compressive, so that's a free parameter. And I showed this plot to Mark, and he was like, well, so what? Like, more is more, you know, like higher star formation rate, higher mass, like you get a correlation. It's not impressive. So then I was like, well, what about the efficiency, Mark? Yeah, and there's efficiency. So again, there's no fudge factors here. So we don't plug in this epsilon naught at all. So the PDF alone essentially dictates what we get on the y-axis here. And of course, the x-axis is different observations from different groups. So in some of these clouds, there's some disagreement with the observers, but you still get a very, very nice, I think, correlation between what the observations predict, even though the error bars are quite large, and what our analytic model would predict. So I think this is a really big step forward, especially for cosmological simulations, which are putting in the efficiency by hand. Perhaps now we can directly use the physics of individual clouds to predict a dynamic efficiency in these sorts of simulations. Now, this is a conference on magnetic fields, and it's like sacrilege that I haven't even mentioned magnetic fields at this point yet, so I'd like to address what I think the role of magnetic fields in this story is. So one, with the efficiency, I think magnetic fields essentially slow down star formation. That's one of the big contributions, and we know this from numerical simulations primarily. This is work done with David Collins, where we took the ENSO simulations with different magnetic field strengths and looked at how their power loss slopes in their PDF evolved with time. So that's what these different points here. The blue points here are the weak magnetic field runs, so highly super-alphenic simulations. And you see that the power loss slope becomes flatter much quicker than in the strong field case. So essentially, in this analytic model picture, star formation would be dramatically slowed down. What about the critical density for collapse? I think this is another place where magnetic fields are extremely important, and I think we'll hear a lot more about this from Dick in the next couple talks. So from the Zeeman data, we see this really beautiful relationship between the column density, the magnetic field, or you can also look at this in a volume density sense, where you see a transition from clouds in the H1, which are subcritical, which essentially just means the magnetic field prevents collapse from occurring. So the magnetic flux would be too strong to have any sort of collapse in these clouds. And you see that as you go to higher column densities, you get this transition under this line to supercritical, where the field is too weak to prevent collapse. This density of 10 to the 21, 10 to the 22 is roughly the critical column density, or related to the critical density for collapse. So there's something interesting going on here with the magnetic field. We can, of course, study this again with simulations. We did a set of Arepo moving mesh simulations with different magnetic field strengths with Philip Motz, so he might talk a bit more about these simulations in order to study this effect. And so in these simulations, we have an enormous spatial and density dynamic range, and we can follow a region of 5 parsec box all the way down to 100 AU scales and study how the collapse is affected by the magnetic field strength. We did 4 runs, so these 3 here I'm showing you all had initial conditions which are either super or transalphenic or supercritical. So we expected collapse essentially to happen in these runs. We did 1 run which was initially subcritical, so we shouldn't expect collapse under ideal MHD, yet we still saw this nice collapse proceeding. And how to explain this, I think I'm running out of time, but the collapse in the super-alphenic, supercritical cases essentially happened at the post-shock density. So this is what you'd expect for the hydrodynamic sorts of initial conditions. But in the case of this subcritical run, the high magnetic field strength, the collapse did happen eventually, but it took higher densities in order for this to occur. And we have some work in preparation with Alex and with Philip to try to describe this in connection to this reconnection diffusion time as related to the free fall time of the collapse. And I think I will just skip this because I'm running out of time. But suffice to say that if you consider the time scale for reconnection diffusion and equate that to a free fall time, then you can calculate a characteristic density for collapse. And it turns out that that density is actually well predicted for the particular initial conditions of the simulation. So talk to me more about that. I'd be happy to discuss it further. And I will leave up the points I made here and take questions. Thank you. Denshaw.
So, as a rough approximation, you could actually include the magnetic fields in your alpha, and therefore, would that change your plot where you had the theoretical star formation rate versus observed star formation rate?
Yeah, so that's an interesting point.
A little bit of scatter out there. Maybe you could.
Are you talking about the virial parameter calculation? Yeah, so in all of those cases, the virial parameter is not really well characterized in those clouds. So that would be something interesting to look into. A lot of times we assume like 1 to 2, but yeah, that would be interesting to calculate further. Yeah, Mark.
So can you put your epsilon FF plot back up?
Uh-oh.
Possibly.
Yeah. Let's see. Oh, there it is.
Yeah,
Okay.
So it seems like a lot of the correlation there is basically coming from that 1 million.
Well, so even if you ignore that point, I mean, the fact that there's no sort of fudge factor at all in there, I think is still very encouraging. Like, even if you would ignore that point.
Sure, but the correlation, like the claim that there's, I guess all the dynamic range is in that 1 point.
Could you please use a seat mic so the people on the webinar can hear? Thank you.
Oh yeah, I forgot to mention, press your button so that the streaming people can hear the questions.
All right.
Yeah.
I'll repeat the question. So the question is, the dynamic range in that plot is basically all in that point chameleon 3. So the question, I guess, is what's special about chameleon 3? And is it, are you, what's driving the theoretical prediction? Is it that there's no power law part?
Right.
Or is
so a lot of these clouds, like chameleon 3 and Musca, well, Musca, like, I've been talking with a lot of the observers that made these measurements. So essentially, Musca has a very low star formation rate, as does chameleon 3. But people don't quite agree on certain properties of the clouds, which goes into the error bars here. On the theory side, the efficiency is essentially driven almost entirely by the measurement of the power loss slope, right? So again, what I'm computing here on the x-axis is quantities that have been observationally measured, and I put them into the analytic model. So the theory also, this has all the error bars associated with the observational measurements as well. So to just re-answer your question, this here is being driven entirely by essentially the power loss slope, like how steep or how shallow that is.
Okay. Let me suggest another point you could maybe put on that plot that might be very useful to give you a bit more dynamic range is the brick.
Oh yeah, okay.
In the central molecular zone,
Right.
because that would give you, I think, significantly more dynamic range. And I mean, if it falls down there by chameleon 3, you're golden. But it would be a good test.
Okay, I will check. I will ask you which papers you think I should look at for the efficiency measurement.
Okay.
Yeah.
I'm afraid we should probably wrap it up. Maybe if there's, while you're changing positions, if there's no quick question. Okay, thanks enough. I knew I couldn't remember the words. By the charge and magnetic reconnection mediated by plasma.
Thank you very much. Can you hear me? I did that on my thing. So, yes. Okay.
Good morning. For those of you who do not know me, I'm Amitava Bhattacharjee. I teach in the program in plasma physics in the Department of Astrophysical Sciences at Princeton, and also serve as head of theory department at the Princeton Plasma Physics Laboratory. I'm here for a sabbatical year, one of David's various bullet points, and it's an exhilarating place to work. I'm having a really great time, and I'm very thankful to Blakesley for organizing this very nice workshop, which fits in nicely this year. So I'm glad to come here and talk to you about magnetic reconnection. There is more plasma physics in it than you might care to know, but nonetheless, something that has, I think, significant implications for what you are studying. This did come up near the end of Blakesley's talk, but due to lack of time, she could not go through it very quickly. So what I'd like to talk to you about are things of macroscopic extent, very thin current sheets that generally form and are seen not only in simulations but also in observations, at least indirect inferences on multiple scales. I should, before I get into the physics of it, acknowledge my collaborators who have helped me study the stability of thin current sheets and the magnetic reconnections that come about, colleagues from Columbia, Princeton, Harvard, as well as the Princeton Plasma Physics Laboratory. The classic model for understanding fast reconnection in space and astrophysical systems had their origins in the sun. Eugene Parker was trying to understand why solar flares proceed as rapidly as they do. The typical time scale was of the order of hours to minutes. And if one looked at the resistive diffusion time scale in these problems, it's much too long. He understood that, and he came up with a simple steady state model whereby magnetic fields which point in opposite directions reconnect across a neutral line. They proceed at a reconnection rate, which is measured by the inflow velocity coming in to the current sheet. And by simple conservation laws that I won't go into the details of, he derived this critical relation, which measured the reconnection rate, scaling as 1 over square root of the Lundquist number. The Lundquist number has eta Spitzer in the denominator, so it is a very large number in general for many space and astrophysical objects of interest. This provided a compass for our thinking on magnetic reconnection for nearly 50 years as the one true model that seemed to have been supported by laboratory observations, simulations, well verified, until about 10 years ago when we realized the model had a fundamental flaw overlooked by Parker, which is that if you have large-scale current sheets, then they become unstable. Well, there's also another feature that steady-state models cannot explain, which is that, and this has nothing to do with Parker, he did the simplest thing, the steady-state model, that in many cases where magnetic reconnection plays a role, you really have a transition from a slow evolving state to a rapid impulsive phase. And that transition must also be the feature of a time-dependent model. And such impulsiveness is seen in a number of contexts. I have a little movie for you to just see. This is not simulation, but spectacular observations from the Solar Dynamics Observatory. It's a real challenge for any codes to reproduce this level of detail. Undoubtedly, they don't resolve thin current sheets at these Lundquist numbers, but there's telltale signature that magnetic reconnection is playing a very important role in these types of observations. That movie in real time is of the order of 10 to 20 minutes. And you can keep on watching it. It circles over and over again. In the Earth's magnetotail, where you have in-satellite measurements of magnetic fields, you have a ubiquity of magnetic island generation, as was done by my postdoctoral colleague, Li Jian Chen. She's now at NASA Goddard in this Nature Physics paper, that she, in fact, through a conglomeration of satellites, cluster, in fact, the European-US collaboration, tested the magnetic field distribution in these cases. And in fact, looking at the signatures of BZ as a function of time, if you cross this, as you can see, there is a bipolar signature. She actually mapped out a whole range of electron fluxes particle energizations as a function of Bz. And what she noticed, in fact, is that you have electron bursts, particle acceleration very rapid, associated with bipolar Bz, which gives you the signature of field reversal in magnetic islands. And you see density peaks. The interesting observation that came out from her work was that the particle energization, even though the maximum energies are seen at the so-called X points of magnetic islands, where the electric fields are the largest, the number of particles that are actually accelerated are much larger at the O points of magnetic islands within. And this, in fact, drove the idea that if you have a thin current sheet, and if it can break up into magnetic islands, that will provide a major accelerator for accelerating a very large number of particles, impulsively too, as seen here. What I want to show you here is how our understanding has changed. And it is not that these sorts of behaviors weren't seen. There's Russian literature, there's German literature that goes back, which made the observation that thin current sheets can in fact become unstable. But a really important analytic progress was made by Nuno Loureiro at MIT, who in fact identified a superalfanic instability associated with very high Lundquist number current sheets. And what happens in these cases, you get a transient Sweet-Parker state very rapidly once you exceed a certain critical threshold in Lundquist number, where it breaks up into these magnetic bubbles or plasmoids that then coalesce, go into a hierarchy of formation, which is self-similar, which you can actually study, and I won't go into that in any further detail other than to tell you that this actually leads to a new result within the context of this simulation and similar simulations. And by the way, this is not just true in MHT, it's also true in collision-less models or Hall MHT models. You see such tendency for formation. What you're seeing here is that reconnection rate time scale. This is the Sweet-Parker scaling, which, as you know, goes up as Lundquist number, which can be very, very long. Sweet-Parker scaling wasn't even enough to explain flares. So we knew that there was a gap in the theory. And what you find here is that in this problem, that you get a deviation once you cross this critical Lundquist number, and the reconnection rate measured either through the Mach number or through the rate of destruction of flux scales like 0.01 VA, which is independent of the Lundquist number. There is analytic theory that goes along with that, a model, I should say, which explains this result, which I don't have the time to go into, because I want to move on to 3D effects, which would occur if you actually take that system and go out in 3 dimensions. And if you do, what happens is that the plasmoid generation that you saw is like a Jackson-Pollock painting in a way. What you see is the island form, but the 3D-ness of it leads to the formation of so-called flux rope type structures, which twist and extend. And then as the magnetic islands grow in magnitude, they overlap, the field lines stochasticize, and you get the appearance of turbulence characterized by power laws. Therefore, plasmoid instability driving the system can lead to the generation of power spectra. And you can actually see this. If you should project on the XY plane, you see blurred structures that will be reminiscent of the 2D pictures, but they're much more blurred now. And if you look at the 3rd dimensions, you see island overlap, and you definitely see things such as these develop. And if you go back and look at heliophysics or solar observations, you will find semblance of this, density blobs and so on and so forth, that we have counted, done statistics on, things that I don't have the time to go into. But there appears to be some correlation, and I say this cautiously because magnetic thin current sheets cannot be seen even by the Solar Dynamics Observatory. So we're using density blobs as proxies for magnetic islands. And whether that is true or not, I don't really know, but that is what we are doing. So getting back, if you look at the reconnection rate, though, what is interesting is they can compare with Sweet-Parker, you can compare it with 2D plasmoids, and you can compare it with 3 dimensions. What you find is that the reconnection rate preserves this feature, that you go to the 3rd dimension is still weakly dependent on the Lundquist number, but the magnitude doesn't change all that much. In short, then, within the realm of resistive MHD, our work has not produced reconnection rates of the order of 1/10 of the alpha n speed, which seems to be everybody's favorite number, but it's 0.01. You can accelerate that further by using collisionless mechanisms, particle and cell simulations, Hall image mechanisms, which throw plasmoids, show higher reconnection rates, those due to intrinsically collisionless mechanisms. But one of the things that I want to show to you is that the 3D mean flow is a lot like Sweet Parker. You get an enhanced channel. That's why you're seeing larger reconnection rates. But if you look at the current sheet widths, you actually find that they do not broaden. In fact, the width is still controlled by the dissipation in the problem. So here you have a system where the effect of turbulence does not seem to be representable by a simple enhancement of resistivity. It is not that. The resistivity, this is something that is quite non-local, and we have worked out a theory for it. Again, I don't have the time to go into it. What you really find is it's a theory that actually conserves magnetic helicity, dissipates magnetic energy, keeps the current sheet at its original length, but enhances the flow channels. We can characterize the turbulence using Chov-Vishniak structure functions, and I don't want to get in the details of that. What you really find, though, that in these simulations, in the so-called critical balance regime that Goldreich and Sridhar made parallel, what we find is that our reconnection, our scaling laws deviate significantly from the critical balance results of Goldreich and Sridhar, K parallel of the order of K perp to the 2/3. In fact, we see K parallel going like K perp. Remember that this system is one where we start out with a highly inhomogeneous system which became unstable to plasmoids, produce stochastic field lines and turbulence, not the classic systems that Goldreich and Sridhar studied with uniform magnetic fields and things like that. Inhomogeneities, temporal intermittency makes a strong case for deviation. And in fact, our scaling laws are not, therefore, as we evolve in time, going like K minus 5/3 at all, more in the range of this for the time scales that we have actually calculated. There is an enormous time dependency in our simulations. We did not run them all the way to steady state. And there is a reason for it as well, is that when we went to, and this actually takes me to the next part of our work, which is that what sets the dissipation range in Kolmogorov turbulence? What we do is to generally say that there is a dissipation range, and as you know, Goldreich Sridhar made the very important point that you have an anisotropic spectra. There is some difference of opinion, of course, between Boldyrev and Goldreich on this particular matter. Let me not debate that issue. It's been extensively debated in the community. What I'm actually pointing to is something subtler than that particular debate, which is that do you have persistence of this range all the way to the dissipation range? Now, if you look at the picture that Boldyrev invoked, is that he had extended current sheets with different extents along length and widths. And now think of these as current sheets, which, when they reach a particular aspect ratio, become unstable to the plasmoid instability. What therefore happens is the disruption of that current sheet before the energy cascades all the way to the dissipation scale begins the inauguration of a new range in scaling law. We have worked that out. In fact, the analytic prediction was made for three-dimensional models, and it was done in a sequence of papers. Actually goes back to Carboni's work in 1990, but preceding us, there's Boldyrev and Loureiro, Mallet, but I believe Comiso did the most rigorous analysis of this, including looking at the feedback of turbulence and current sheets back on turbulence, the feedback problem in a way that in a different way Blakesley was emphasizing. And if you run to these simulations, this is now only 2 dimensions because we are not able to do this at this level of resolution in 3 dimensions yet. Exascale will enable us to do that. This is one reason to go to exascale computing, which is around the horizon. But if you go to these very high magnetic Reynolds numbers, you see clear evidence of plasmoid structures. If you should run the same simulations at lower values of the magnetic Reynolds number, you do not see them. And you do not see the phenomenon that I'm actually talking about, which is a formation of thin current sheets and the interruption due to plasmoid instabilities. We find, therefore, that the picture of inertial range spectrum needs to be modified. One, there is, in fact, an inertial range, -3/2 in our case. Then there is a dissipation range out there, but there is an intermediate range, a K-star range, where, in fact, the deviation from the inertial range spectrum is not a pure power law. We have calculated that. Power law multiplied by logarithmic corrections that are very hard to verify numerically except in 2D, but the theory is definitely now more precise as the result of it. Therefore, my time is out. I just want to tell you the thin current sheets extended are very fragile and spontaneously unstable to the plasmoid instability. The discovery of the plasmoid instability, I believe, has been important in the life of reconnection theory. It certainly stimulated a bunch of laboratory experiments. The energy spectrum actually steepens with respect to the inertial range due to the interruption of plasmoids. This occurs at relatively small scale. And in this plasmoid-mediated regime, our spectral index is close to minus 2.2, similar to what we saw in our flux rope simulations as well, albeit in 3D. The extension to 3D is really an important next step, awaiting the next generation computers. Thank you for your attention. Blakeslee?
Really nice work. I'm wondering, so one of the predictions from the Lazarian-Vishniak model is, of course, that the reconnection rate scales with the properties of turbulence rather
Can you
than
please use your seat mic, please?
So I'm wondering if you've checked like things like resolution and box size, and does that change the power spectrum at all?
First of all, in the two-dimensional cases, we do an extensive checks, and there's also an analytic model.
But in the 3D,
That, of course, does
you
not
showed the
depend.
first results you showed were the 3D results. Yeah.
The first results were the 2D results. The next results were the 3D results. And what we actually did was did a similar test of the kind that we did in 2D numerically. And we find the same results. This doesn't disagree with the Lazarian-Vishniak prediction that the reconnection rate becomes independent of the Lundquist number. It just is that in our MHD models, even in the turbulent cases, we get an order of magnitude lower reconnection rate, which is 0.01 VA. The only way we will get to 0.1 VA is by running things through a PIC code or a Hall MHD code, which gives you this higher rate. So in that respect, our quantitative prediction is different than Lazarian-Vishniak. But we also are looking at a different system than the one that they studied. I think Alex had his hand up first, Ethan. Between you guys, you can decide who wants to ask. Up to the chair of the...
Okay. All right, I'm live. So about 6 months ago or so, I read your paper. I liked it very much. But I also looked up a bunch of other papers that tried to do the same three-dimensional thin current sheet problem. And to say that there's a strong discrepancy between them would be...
I didn't say there was a strong discrepancy.
No. I'm saying that other people who've tried looking at the structure of spontaneous turbulence in a thin current sheet got very different kinds of results. And I wondered if you could say a few words about that.
So, I just want to get to the references I cited, which I think may be a good point. These are the references. Between Boldarev and Loureiro, Mallet, and us, the difference is one of logarithmic terms, which, by the way, are not of order unity. They're factors of 10. To a zeroth order, therefore, we are in agreement with them, but they didn't do a complete calculation. So I'm not completely sure. These are the papers which I saw, looked at that, but tell me which others you have in mind. Did they also do?
So there was a paper, I can't cite them all. There was a paper by McLeod. There was a paper by Berezniak. I'm sorry? Koval. I'm blanking on a Japanese name. Takamoto, thank you. These all looked at, with different boundary conditions, thin current sheets, MHD, three-dimensional.
What RM?
Let's see, I wrote them down at one point, but they all seemed vaguely comparable.
We have two classes. Like, we run them at 10,000, you see nothing. We ran it at 1 million to see it, and we could do it only in 2D.
No, these are all 3D.
Well, therefore, look at the resolution and look at the magnetic Reynolds number.
No,
I'm telling you that doing them in 3D is really outside of the reach of present-day computers. So people could only have done it at low magnetic Reynolds number.
But you've also done 3D calculations.
Sure.
Showing the plasmoid instability.
Right.
And saying they tried to do the same thing with comparable resolution to what you saw, and they get just Goldrake-Sridhar turbulence generated from the current sheet.
Let me explain again. I too will get gold, and this. Forget about this simulation. Let's go to this one. At sorry, at this Lundquist number, 10 to the power 4, no plasmoids.
Yeah, no, but this is
And
2D.
no change.
Yeah.
Yeah. Well, this whole issue of whether 2D MHD teaches us something about 3D MHD, it teaches us more about 3D MHD and MHD than hydrodynamics, where 2D and 3D are profoundly different. Until I do the 3D problem, I don't want to say what we will see. It needs to be done.
But nature is three-dimensional, I'm sorry.
Nature is three-dimensional.
Yeah, and we will not be able to breathe if we...
Yeah,
This is a
right.
good moment. We can discuss.
Yeah,
it
we can
over
continue
discussion.
this.
That's a wonderful.
Thank you very much.
Very impressive calculations. Okay, next up is Richard Crutcher.
Spectrum of a flame in the presence of a magnetic field, and he finds that the line is broadened in comparison with the width as shown by those two lines in the presence of a magnetic field. Almost immediately, Lorentz explained that using classical physics in terms of an electron in orbit around a nucleus in the presence of a magnetic field. And he made some predictions, namely that the original spectral line would be split parallel to the magnetic field in two components that were circularly polarized and perpendicular to the field in three components that were linearly polarized. And at the importance of that, at least in physics, was it enabled one to estimate the ratio of the electron charge to mass. Well, the polarization was a new prediction, so Zeeman went back to his laboratory and did the same experiment, but this time using a circular polarizer, and found that indeed the right and left circularly polarized lines were shifted, and measured a value for this charge to mass ratio, which is not too bad in comparison with modern values. They were awarded the Nobel Prize in Physics for this work, mainly for this reason. The prize didn't even mention the possibility of the future crucial role for the Zeeman effect in measuring astrophysical magnetic fields, although Zeeman had suggested that in his original paper. The first astrophysical detection was in sunspots by George Ellery Hale, and then not in the interstellar medium until 1969 by Verschuur in the H1 21 centimeter line. And this just summarizes some of that in a simple two-level atom without a field. You have a spectral line in the presence of a field. You get the Zeeman splitting. The splitting is proportional to a number Z, which I'll call the Zeeman splitting times the total magnetic field strength. For H1 at least, the 21 centimeter line, this Z is the Bohr magneton. And for other atoms or molecules with unpaired electrons, it's comparable to that. And this just illustrates what I said a moment ago, the polarizations you get parallel and perpendicular to the field. Now, if you can measure all of this, you can infer the full magnitude of the magnetic vector, the magnitude in the plane of the sky along the line of sight, and the position angle. Unfortunately, in general in the interstellar medium, the Zeeman splitting is a lot less than the line widths. So here's a Stokes eye spectral line.
Here's what will happen in the case of the Zeeman splitting. But if this splitting is a lot less than the line width, then you get all of this blended together. You can still measure the magnetic field in the line of sight from the Stokes V spectrum, just the difference between left and right. This is an example of this line with a Zeeman splitting of 1%, and you get about a 1% Stokes V signal. In the case of Q and U, the linearly polarized Stokes parameters, because you see all three of these, when you measure these parameters, you get a vastly weaker signal. It's proportional to the splitting squared now, and since this is, in this case, 1% of the line strength, that becomes 10 to the minus 4. So for practical matter, you can only measure the magnetic field strength along the line of sight. It's also true that to have a strong Zeeman splitting, you require an unpaired electron spin, and most of the interstellar molecules that we see, CO, HCN, et cetera, don't satisfy that criterion. So there's actually only 5 species for which a clear Zeeman splitting has been detected, with OH being detected both in the extended gas and the masers. Fortunately, those sample a pretty wide range in density, so it's possible to explore the magnetic field strength as a function of density. I'll show you a couple of examples of the data. This is the Stokes V detection experiment in OH toward Orion B. It shows the distinct Stokes V signal with the prediction and the observation superposed. Some 15 years later, we used the VLA to map the Zeeman effect toward this object. This shows the Stokes I and Stokes V signals at the peak of the magnetic field strength. You might notice that the sense of the Stokes V signal is reversed in these two. That's because that sense tells you whether the field is pointing toward us or away from us. And soon after we published this result, Carl Hylas used the 85-foot telescope at Hat Creek to measure the Zeeman effect toward that object, and noticed that we'd made an error in the sense of the polarization. It turns out the engineers at Nancy Observatory had told us that left was right and vice versa. Another kind of interesting fact about that is that when Zeeman first published his work, he made that same sign error. And so initially, he announced that the charge of the electron was positive. But once the polarizations were straightened out, that error was fixed. So this is NGC 2024, sometimes called the Flame Nebula. It has a nice dark lane through it. These black contours show the extent of the molecular cloud as mapped in C18O, and the color scale shows the map of the magnetic field ranging from about 100 microgauss on one side to essentially 0 on the other. The yellow line segments are dust polarization observations by Hildebrand et al. With a magnetic field perpendicular to those. So the magnetic field seems to sort of wrap around this dark molecular column. A more recent result is shown here. The background image is from Hull et al. And shows karma observations of CO, showing this bipolar flow from W3OH. This is an ultra-compact H2 region. This is a very dense molecular core. They also mapped the dust polarization, and these green line segments show the direction of the field. So the field is across this core, more or less horizontal. It shows what looks like sort of half of an hourglass morphology, but the northern half wasn't observed, well, wasn't detected. We used the ERAM 30-meter telescope to map the Zeeman effect in the CN 2-to-1 transition, and also used karma to do the same thing, combined the two so we'd get full spatial coverage. And these black contours show the result of that, with the field reaching close to 3 milligauss pointing away from us on one side, and about 2 milligauss pointing toward us on the other side. Again, it's consistent with the field kind of in this direction, kind of wrapping around this more or less north-south distribution. So why does one care about measuring magnetic fields in star-forming regions? Well, one very important parameter is the relative importance of gravity to magnetic support, which is parameterized by the mass to magnetic flux ratio. Each of those can be measured if you can measure column density and magnetic field strength. The Zeeman effect giving you this. The critical value for those being equal is given in at least one model by that. And so a number less than 1 is subcritical, means the magnetic field is dominant. Greater than 1, supercritical. This is a plot which Blakesley showed a version of. It has survey results from a large number of people at low densities. H1 is the sampler, at intermediate densities OH, and at high densities CN. And since this was first published, Thomas and Troland have added some points in OH absorption, which a little bit fill in this bit of a gap between the H1 and the OH. The implications of this are that lower densities, the interstellar medium is subcritical in this region right here. For a column density of about that, even though B is increasing, the mass to flux ratio is now supercritical. And there are no clearly measured subcritical molecular cores. Now this is, at first glance, consistent with the model of star formation, especially popular maybe 20 years ago, that you started out with subcritical clouds supported by the magnetic field, and that as a result of ambipolar diffusion, that is neutrals collapsing via gravity through the field, you could build up a supercritical core. Two problems with that is that these clouds are not gravitationally bound. And so the physics in going from here to here cannot simply be gravitational collapse changing from subcritical to supercritical. The gravitationally bound objects are primarily over here, and there are no clearly observed subcritical clouds, which is what that theory would predict exist. Another thing that one can do is try to measure the change in mass to flux ratio from the core to the envelope. And the problem is always that the Zeeman effect only is measuring the line of sight component of the magnetic field. But for a relatively uniform field, the angle between the field and the line of sight is the same. And so you can divide that out and actually measure the ratio between the core and the envelope of the mass to flux ratio. This is a result we obtained for 4 such cores. In all cases, that number is less than 1. This ambipolar diffusion model requires greater than 1. One thing that can predict this result is turbulent reconnection, since the field strength is reduced in the cloud envelopes where turbulence is strongest. Ambipolar diffusion fans, as you may be aware, strongly challenged this interpretation for various reasons. I'm not going to go into that argument, but one thing I might point out, originally I think Dan Clemens was supposed to come, but he ended up not coming. He's been carrying out observations toward clouds, including, for example, this one, using dust polarization to infer magnetic field strengths as a function of radius in clouds. And at least toward L1544, he gets the same result that we did, namely that that ratio is significantly less than 1. And so hopefully he will continue that work and publish further such results as time goes on. Final thing I want to talk about is scaling of field strength with density. This shows several simple scenarios. Collapse along the field produces no change. It produces an exponent of 0. If you compress perpendicular, the exponent is 1. This ambipolar diffusion model has initially collapsed along the fields to produce a disk, and then contraction perpendicular to the field due to ambipolar diffusion. So this number is expected to change from 0 to gradually approaching 0.5 with a typical value of around 0.3 or 0.4. And Mestel, many years ago, when he first started thinking about these things, predicted an exponent of 2/3 his particular calculation was based on spherical clouds with a very weak magnetic field. This number does suggest a weak field, but it doesn't require a spherical cloud. It only requires homologous collapse. So here's basically the same data that was plotted before against column density, now plotted against volume density. Thomas and Trollin didn't attempt to infer volume densities for the data which would fall in this range. What we did was attempt to correct for the fact that you only measure the line of sight component of the field by putting in a model for the distribution, the PDF of the field as a function of density, and used Bayesian analysis to infer the parameters of a model. So the model at low densities where these objects are not gravitationally bound has the same absolute magnitude, the same maximum magnitude of the field, independent of density. But the PDF we found was essentially uniform. So some of these clouds have very weak magnetic fields. There's a transition point where the field starts to increase, and the slope we found was of order 0.65 with that kind of uncertainty. Okay. Finally, masers, as I mentioned at the beginning, can be used to study higher density regions. These are figures taken from a paper by Vlemings. This shows a methanol maser result, the Stokes I and the Stokes V. The splitting is not enough to clearly see the two separate sigma Zeeman components. So you do the same thing that you do for non-maser lines. He infers a magnetic field strength of about 15 milligauss here. And he, in that paper, plotted ranges of density and magnetic field strength for the combination of OH and H1 at low densities, and then these various masers. The CN Zeeman wasn't available at the time he did this. These points are for a specific source, but he did fits to all of these data and found an exponent of about 0.5. Two problems that one should note with regard to masers is that their densities are very uncertain, really. They're based on theory of maser excitation rather than any more direct measurement. And at least in some cases, the Zeeman splitting factors are rather uncertain. So he gets 0.5. What I did was take the slope that we had inferred from the non-maser data, which covered the range from here up to about 0.6, and just extended it. And so, given especially the uncertainty in these numbers and the fact that we would suggest that there's a change in slope here, I don't think that one can argue that's really an inconsistent result. Whether the slope in maser regions should be related to the slope in more extended regions is another question entirely. But at least the data themselves are consistent with a slope of a order of, say, 0.6. Okay, so obviously what one would like to do is see how magnetic field measurements, Zeeman measurements, what they tell us about star formation scenarios. One scenario is that the magnetic field is very weak, that turbulence controls everything. And several reasons that I think argue against this picture is that B is observed to be quite strong in the diffuse interstellar medium. It's not weak. And based on dust polarimetry, it's my view that the field morphology is generally fairly regular, not chaotic, which a very weak field might suggest. A strong B without turbulence, the so-called ambipolar diffusion model. As I mentioned before, there are no observed subcritical self-gravitating clouds. The exponent in this relationship is observed to be greater than 0.6, and the model predicts less than 0.5 and more typically 0.3 or 4. And the mass to flux ratio is observed to be the opposite from the prediction. The picture that I think is consistent with all the observations is a relatively strong B with turbulent flows and magnetic reconnection. You will have turbulent flows, preferentially along the magnetic field, with magnetic reconnection helping to keep the magnetic field more or less constant until objects become self-gravitating. So what are the next major steps in this game? Well, I think variation of field strength as a function of volume density within a single cloud complex in order to study this relationship would be very valuable. One criticism of the things I've been talking about is that the sample is very heterogeneous. You're not following the evolution of a single object. You're comparing a wide variety of clouds. And if you could start doing that within single clouds from envelope to core, I think that would be more compelling. And the same thing is true about the mass to flux ratio variation, which we started to do with those 4 objects that I mentioned earlier and that Dan Clemens is starting to do. What I think really is needed is to take all of the measurements of interstellar magnetic fields, because no single technique or even all of the techniques together will give you a full measurement of the magnetic vector. But if you take Zeeman measurements and linear polarization observations of dust and spectral lines, the so-called Goldreich-Kalafis effect, plus velocity and intensity gradients that Alex has pioneered, you can probe, not fully measure, but probe the 3D structure of the magnetic vector. And then, since this is a computational astrophysics institute, I should point out that we really need detailed computer simulations to compare with the observables. And we also need new Zeeman observers, the people who mainly produce the observations I'm talking about, like Carl Hylas and myself and Tom Troland, are all over 70. So we need some new blood, and new telescopes such as ALMA, FAST, and the SKA might make that possible, although as you're probably aware, ALMA in particular has severe instrumental polarization problems, which make this kind of work difficult. Thank you.
Thanks a lot. The guys who started the clock started slow, so you were seeing something that was running slow, so we actually don't have more time for discussion.
Oh, okay.
Unfortunately. Sorry.
Okay.
I was trying to give you the right signal, but you
Oh,
were confused.
okay, sorry.
But there'll be plenty of time in the discussion this
Okay,
afternoon.
that's good. I don't get to be asked any embarrassing questions then. It's always good.
You're hoping they'll forget. Okay, so next, the next talk is by Philip Moe, Shock Structures and Magnetized Supersonic Isothermal Turbulence. And let me compliment you on the magnificent observations that you all are doing.
Oh, you have one?
Oh, mhm.
Thank you.
Yep, is it on?
Just push that one button. Yep, you're good to go. Forward and back.
Yeah, thanks. Okay, hello everyone. I'm Philip Motes, and today I'll be talking about something short and simple: shock structures in idealized simulations of magnetized supersonic isothermal turbulence. I'm at Princeton University this year as an Einstein Fellow, and this is work I've done in collaboration with Blake Sleeper-Cart. Okay, so first, let's talk about the context of what I'll be talking about. These are idealized simulations of isothermal turbulence, and they're characterized by just 3 parameters, so it makes it a very nice toy model to study. They're characterized by the sonic Mach number, so in the context of star formation, these supersonic Mach numbers might be around 10. They're characterized by the alphanic Mach number of the turbulence, or alternatively the plasma beta. And then there's also an invariant that's associated with the mean field that you put in the box. So the mean plasma beta, the plasma beta for the mean field is a constant. And finally, there's you switch on self-gravity, so a cloud complex like this might have some real alpha parameter associated with it. So if you're studying a giant molecular cloud scenario, that's about to collapse and form stars, then this value might be around 1. So the most interesting parameter to explore among these three, the least observationally constrained, is the magnetic field strength. Okay, and then there's some strengths and weaknesses of the model I want to highlight. So a strength is that these turbulent models are consistent with the line width size relation seen, and Larson's law seen a long time ago, that indicate that the interstellar medium is turbulent. The ISM is thought to be approximately isothermal through collisional heating and radiative cooling effects. And these supersonic turbulent models produce a log normal PDF that's observed. And once you switch on self-gravity, then these you collapse to form isothermal cores, and this creates a power law tail, which Blakesley talked about in her talk today. And you can use this model to make quite realistic IMF predictions through various approaches, including the excursion set model by Phil Hopkins. And such models can predict relatively inefficient star formation rates. There are some weaknesses of the model, of course. It's very idealized. I've ignored important effects such as feedback and radiation. Radiation is particularly important for massive stars. And then there's also non-ideal effects of MHD that have been ignored. So there's no resistivity here. There's no ambipolar diffusion occurring. There's also no collisionless effects. And finally, these simulations are disconnected from larger scales, so there's no galactic shear, galactic rotation, etc. But so the big questions I'll be talking about today, particularly the second one here, but let's start with these two, is whether magnetic fields or turbulence can be more important for regulating star formation during the collapse of these prestellar cores. And this is characterized by the alpha-anic Mach number of the turbulence, which tells you whether the turbulent kinetic energy dominates over the magnetic field energy or vice versa. And what I want to talk about today is actually what are these physical dense structures in a turbulent medium that collapse and form prestellar cores, which we can answer by looking at simulations, looking at where density collapses and tracing back to the originating structure with tracer particles, and looking at what these structures are in the context of these two regimes of the model when the magnetic field is strong or weak. Okay, and then this research is motivated by a recent paper by Robertson and Goldreich, which shows they take just some non-self-gravitating simulations with just the fluid equations, no magnetic fields, supersonic isothermal turbulence, and they show that they can identify the densest regions here with these shock structures where you have a strong jump in the density, which scales as the Mach number of the shock squared, followed by an exponential atmosphere. So here's the jump, and here's this exponential atmosphere behind, which can be calculated analytically from balancing the upstream ram pressure and the pressure gradient behind the shock. And so this is indeed the shock. You have a jump in the velocity, you have some converging flow, and such structures are transient. They form in a supersonic medium as you stir it turbulently, and they sweep up material and expand, and then as they expand, this density jump decreases as well by the continuity equations, and then they return back into the to become part of the background medium, and this happens on the time crossing scale of these shocks. And so then the question is, can these structures collapse under self-gravity, and also how do magnetic fields modify this picture? So one of the interesting findings of this paper is that they could go into these simulations and identify the densest regions of the PDF, the density PDF, and they were all found to be associated with shock structures that look like that. Okay, so here's the concept, again in illustrative terms. With some of my simulations too, you might have some shock sheet, and if you have magnetic fields, then maybe you can hypothesize that the sheet might be aligned perpendicular to the magnetic fields, because it's easier to collapse along that direction, and then these dense structures may go Jeans unstable and collapse to form prestellar cores. And the picture here is that isothermal turbulence may be a network of these strong shock sheets that are responsible for prestellar core formation. And so these prestellar cores come from the post-shock collapse region. And this is possible because if you do some calculations of the expansion timescale of these shocks and the freefall timescale of the collapse, they're comparable. So some of these shock sheets might collapse to form prestellar cores, and this is what I investigate. Okay, and this model, it's sort of trying to offer a complementary picture to star formation in physical space. There's also other pictures you can use as statistical description to predict star formation, such as models motivated by cosmology, like the excursion set model, where you might have a statistical description of a first crossing distribution. You keep track of the density perturbation, and once you cross a threshold, a barrier through Brownian motion random walk, you might then trigger formation of structure, and then you can use this model to predict an IMF. But here, I'm trying to offer a complementary picture of what's going on by working purely in physical space. Okay, so we can just ask what happens in one dimension when you have shocks without any turbulence. And if you shock this isothermal medium parallel to the magnetic field, then it's actually identical to this self-similar model. The magnetic field does not do anything. So you form the shock, it quickly develops. You give the medium some velocity kick, you form a shock, quickly develops into this self-similar exponential atmosphere profile, where you have where it's expanding with the sound speed and sweeping up material, and the density jump decreases with time. And if you go perpendicular to the shock, you can have analytic solutions, as I do in my paper, to this as well. Now you break the self-similarity of the solution, and you have initially, okay, the magnetic field now, there's additional magnetic pressure support against the ramp pressure when you go perpendicularly to it. So these are just the two limiting cases. Now with the magnetic field, when the magnetic field pressure is strong, then you break self-similarity. Now you have a different solution early on, and then the jump condition, you have a reduced density jump as well due to the magnetic field, and the expansion is now driven by the fast magnetosonic speed. But then at late times, okay, then the gas pressure, once this density jump becomes smaller, the gas pressure dominates, and then you recover this exponential like solution as well, as in the original case. And then so based on these two limiting cases, you expect the collapse perpendicular to the strong magnetic field to be suppressed. Okay, so now we investigate this in simulations of isothermal turbulence, where you turn on self-gravity and form cores. And again, these are the parameters that I'm investigating. Supersonic Mach numbers of around 10, alpha virial parameters of around 1, and I'm varying the mean magnetic field strength characterized by these numbers. So from very weak all the way through very strong magnetic fields, you collapse. This is a picture Blakesley showed earlier too. You have this 5 parsec box, and you collapse to form structures down to scales of a few hundred AU. And what we found is, okay, so we were able to trace the structures that collapse and also the densest regions of the box prior to collapse, and we could find that they're all we could always identify a strong shock at these cells and fit an exponential profile to the to all these shocks averaged. So this is consistent with the picture. This exponential profile extends for up to at least 1 or 2 scale heights. And even in the case of strong magnetic fields, where actually this picture is even clearer because the magnetic fields ended up helping align the shocks parallel to the mean field. We can also trace so here we have no gravity and gravity. We collapse to form structures, and we can trace where the originating gas comes from, which was used to identify these shocked regions. Again, in the case of strong magnetic field, the originating region now is oblong, and collapse happens primarily parallel to the magnetic field initially. So I'm going to just highlight these shock structures again, which were found. So each of the isothermal cores that we formed in our simulations were associated with these shock sheets prior to collapse. And so in the interest of time, this slide now summarizes what happens to the cores once they form. I won't get into this in too much detail because I have 2 minutes left. But there are some differences when you have strong and weak magnetic field in how the collapse happens. As I already described, collapse in strong magnetic field cases initially along the magnetic field. And this actually leads to differences in how the magnetic field grows with the density. So you have purely self-similar collapse in energy when you look at the energy densities when you have a strong magnetic field, but you have faster magnetic field growth compared to the strong field case when you start off initially with a weak field. And in these models, we also had evidence for turbulent reconnection diffusion in the strong field case. I wanted to put up the slide since it was mentioned several times already by others this morning, where we find evidence that the mass to flux ratio evolves and decreases as you form these cores in the strong magnetic field case. So in conclusion, I wanted to highlight the shock structures that form the prestellar cores. They are consistent with all the prestellar cores being formed from a network of these transient dense shocks that make up the entire the densest region of the density PDF, and they sweep up material and go genes unstable to form these prestellar cores. And in the case of weak magnetic fields, this collapse is isotropic and very similar to the Robertson-Goldreich picture. In the case of strong magnetic fields, it actually the collapse occurs preferentially parallel to the lines, which might have some observational consequences for how these prestellar cores subsequently evolve. So that concludes my presentation. Thank you for your time. Alex?
Could you explain the difference in terms of being not self-similar?
Can you please use your seat mic?
Oh, I'm sorry. Could you explain the difference in terms of being self-similar or not self-similar in the case of this strong or weak case collapse? What makes one case self-similar and one is non-self-similar?
Oh yes,
And,
okay, yeah.
and the related question is, how do you treat turbulence in this self-similar solution?
Okay, yes. So I did not get a chance to explain what I mean here in detail. Let's see. So this was this goes back to my previous work in 2007, where we looked at the energy densities of these cores as they collapse. And what ends up happening, by self-similar, I mean what we find is that the kinetic energy density and the magnetic energy density is in equipartition as this core collapses. And this is only true in the strong field case. We have roughly plasma beta is equal to 1 anywhere in the core as you form it. And to have self-similarity, you basically you basically need a scaling that beta goes as rho to the 1/2, because if you have faster field growth, then the magnetic energy starts dominating over the gas pressure, and you cannot have self-similarity in the energy densities.
But what about turbulence?
Okay, yeah, turbulence is interesting. So perhaps perhaps it's not self-similar in the sense that the mass to flux ratio changes in the core as you look at the core compared to the envelope. So don't take this well, I have to define what I mean by self-similar here. Yes. Mm-hmm. Okay, questions?
Can you use your seat mic, please?
Argos morphology is that if you look at spectra, then they're strongly anisotropic in the second case and isotropic in the first case.
Oh, Mark?
Okay, so I'm going to ask the question all numericists hate. What about convergence? The reason I ask is because we did some convergence studies without magnetic fields in just hydrodynamic collapse. And what we found is that you could not get convergence for an isothermal self-gravitating flow. That is to say, as you increase the resolution, your cores would just break up into smaller and smaller pieces, and it would run away. And your cores were always the smallest things you could resolve, which in some sense is not surprising given that isothermal turbulence is scale free. So
yeah, I mean, yeah, there is actually the solution does go singular. So here the simulations are restricted just to the formation of the first few cores, and I was able to verify that if I have the resolution, I still form the same cores at the same locations. So these simulations roughly go to half of free fall time once you switch on gravity. And at that point, I didn't see evidence for fragmentation, and I saw convergence in the core properties.
But do you think if you ran further at higher resolution, these cores would subfragment, or do you think they would?
Yeah, it becomes hard, but then you're also missing the physics that should be there.
Sure, but limiting it to the isothermal regime.
Yeah.
Do you think these cores would subfragment if you were to run longer, keeping it isothermal at higher resolution?
There's yeah, I guess I haven't done that, but it's possible. I guess that's what you see. Oh yeah, so this is it's an adaptive resolution. It's moving mesh code. So you have let's see, I did not mention it here. So at the centers, so you always resolve the gene scale by at least 32 cells, and you have so you have an effective mass resolution, which I think was 0.001 solar mass. So much smaller than the mass of the core.
Okay, thanks very much.
Okay, thank you.
Yeah, sure. Detected magnetic fields on density filaments.
So how to go next slide? Oh, okay, thanks. Okay. Okay. So I'm going to talk about first the density fluctuations in the SM. Interstellar density fluctuations indicated by radio observations of pulsars because of the interstellar scattering of the radio waves emitted by pulsars. Radio observations of galactic pulsars can be used to measure interstellar density fluctuations. Density fluctuations in the local SM measured by nearby pulsars and density fluctuations measured by high latitude HF emission both show that density fluctuations in the diffuse warm ionized medium follow a parallel spectrum with a cosmograph spectral index. The cosmograph parallel spectrum is a characteristic of incompressible turbulence as a result of energy cascade. Energy cascade means the nonlinear interactions of turbulent flow transfer turbulent energy within a broad range of length scales, and this is called inertial range of turbulence. And from what I showed earlier, that you saw the spectrum, the inertial range of interstellar density fluctuations, they spans over more than 10 orders of magnitude in length scales. So I'm going to talk about a lot large scale and small scales. But when I say small scales, I mean relatively small scale compared to the injection scale of turbulences. It could be on the order of parsec. Within the inertial range of turbulence, the turbulent energy on one length scale is transferred to next smaller length scale within this ideal turnover time, which is defined by this length scale divided by the turbulent velocity across this length scale. And this constant energy transfer rate of turbulence directly leads to this cosmograph spectral index of the turbulence parallel spectrum. So the turbulent cosmograph spectrum of density fluctuations seen in the SM shows that, well, it indicates the interstellar density fluctuations are induced by turbulent velocities. This can be easily tested by a simple numerical experiment. So we start with uniform density distribution, and then we drive turbulent velocities on the length scale comparable to the size of the numerical box. And then we see, so at early time, the density fluctuations appear on large scales and then to smaller and smaller scales, and the density distribution becomes more and more homogeneous. After the simulation becomes statistically steady, we can also measure the spectrum of the density fluctuations. Okay, and we find that the density fluctuations passively follow the same cascade as turbulent velocities, and as a result, they have the same cosmograph parallel spectrum as turbulent velocities. So this confirms that density fluctuations are induced by turbulent velocities. So I showed that in the diffuse warm ionized medium, the density fluctuations measured follow the cosmograph spectrum. But wider density fluctuations measured everywhere in the SM follow the same cosmograph spectrum. Observations show that this is not the case. So this is a collection of spectral measurements in different interstellar phases. We see that in the gas phase traced by H1 emission, this is diffuse warm medium. The density spectrum is cosmograph-like, and this is the same as what we see in the diffuse warm ionized medium. In the cold phases traced by H1 in absorption, CO lines, and dust, And we see that the density spectra become much shallower with much smaller spectral indices. A caveat here is some spectra that stays at the spectral index around 3, and this is pointed out by Lazar and Pogerson. This could be just due to the optical depth effect. It's not real spectral information. So observations tell us that in different interstellar phases, density fluctuations show different spectral shapes. The cosmograph density spectrum in the diffuse warm phases and shallower density spectra in cold phases. The shallow density spectrum means with smaller spectral index, it means there are more, this upper profile, it means there are more density fluctuations and smaller scales compared to the cosmograph spectral form. How can we understand this difference in density spectra in different interstellar phases? If interstellar density fluctuations are induced by turbulent velocities, a simple explanation is that in different interstellar phases, turbulence has very different properties. From warm phases to cold phases, because of the dramatic change of temperatures, turbulence changes from subsonic with the turbulence speed smaller than the local sound speed to highly supersonic with the turbulence speed much larger than the local sound speed. And in the warm phase, the turbulence is subsonic, and we know that subsonic turbulence is similar to incompressible turbulence. That's why the density spectrum measured in the warm phases have the cosmograph spectrum as the same as incompressible turbulence. But in these cold phases, turbulence is highly supersonic, so it cannot be treated as incompressible turbulence anymore. And in these phases, the turbulence is highly supersonic, and the faster supersonic turbulent flows, they induce shocks, and this is already shown in last talk by very nice simulations. These shocks are very efficient in compressing gas and generating small-scale, high-density structures, and correspondingly, the density spectrum becomes shallower. And here there are more numerical experiments done by Kowa et al. 2007, where they simulate different turbulence properties and the resulting different density fluctuations from warm phases to cold phases. And we see that in the warm phases with subsonic turbulence, the density distribution is quite uniform, which is characterized by large-scale density variations. And if we go to cold phases, turbulence are highly supersonic, and these are shocks and they compress gas. The density distribution become quite clumpy, filamentary. And as a result, if we move from subsonic turbulence to highly supersonic turbulence, and we can see the change of the spectral slopes becomes changes from cosmograph-like to shallower spectral forms. So for this part of my talk, I want to make the point that in different interstellar phases, turbulence properties are very different, and as a result, the density fluctuations have very different spectral shapes. And this understanding of density fluctuations in the SM based on our understanding of turbulence is very important, and it looks like this provides the only solution for many long-standing problems in observations of the SM. For example, for the interstellar scattering measurements of galactic pulsars, what is shown here is this is scattering time, and this is due to the scattering effect. And this is dispersion measure, which is an indicator of the distance from us to the pulsar and the mean electron density. And you can see that these observations show that there's a broken parallel scaling relation, and we found this can be well explained by the homograph density spectra in the diffuse warm medium and the shallow density spectra in cold phases of SM. Very interesting that it's not only for interstellar scattering measurements, for interstellar rotation measurements, Faraday rotation, we see the similar broken parallel, and this again suggests a different turbulence regimes and different density spectrum. And they notice that this is spectral index indicated from both observations are in fact consistent with direct measurements, the spectral measurements of density fluctuations in cold phases. Okay, so this is second part. I'm moving to the effect of magnetic field on density fluctuations in the SM. The density fluctuations, okay, so the magnetic effect on interstellar turbulence has been measured in different interstellar phases. In the presence of magnetic field, turbulence becomes very different from hydroturbulence. And the most significant difference is that turbulence becomes anisotropic. And anisotropy depends on the relative importance between the local turbulent energy and magnetic energy. Because of the energy cascade of turbulence, turbulent energy decreases towards smaller scales. So at smaller scales, we can have the turbulent energy smaller than magnetic energy, and as a result, anisotropy of turbulence becomes stronger at smaller scales. And you see these velocity structures of turbulence becomes more elongated along the local magnetic field. So I already showed that turbulence has very different properties in different interstellar phases. To illustrate the magnetic effect on density fluctuations, here I only show example of a particular turbulence region, which is subsonic turbulence applicable to warm phases of the SM. And we start with initially isotropic density distribution in a well-developed turbulence. And here we have magnetic fields with the mean magnetic field direction parallel to the slide. And we see how this initially isotropic density distribution evolve with time. And we again see these density fluctuations developed on different length scales. This process is similar to we drive turbulence in our coffee and the evolution of the cream density fluctuations in the coffee. But the difference is that coffee is not magnetized, but here we have magnetic field. As a result, you see that these density fluctuations are formed preferentially along the magnetic field lines. So to better illustrate this, these are the snapshots taken at different times of the above experiment, and you can see that these there are the parallel, these filamentary structures of density fluctuations are formed along with the local magnetic field lines as superposed on the last snapshot of this experiment. And I want to stress that the anisotropy of turbulence doesn't affect the observed slope of spectrum. This has already been confirmed by observations. So they measured the anisotropies in the H1 gas distribution, and these are the turbulence spectrum measured at different position angles, different colors. So with different position angles, you see the amplitude changes, but the slope always conform to the homograph spectrum. Okay, and to better illustrate this scale-dependent anisotropy, we measure both velocity and the density fluctuations at different length scales. And you can clearly see that at smaller length scales, the structures become more elongated along the magnetic field lines. And this can explain many observations of these parallel filaments in the SM. But again, I stress that this only is applicable to this subsonic turbulence in warm phases. In cold phases, supersonic turbulence, density in the magnetic field is pretty coupled. And as a result, these are, in fact, density fluctuations perpendicular to magnetic fields, as shown in these many simulations and also frequently seen in molecular clouds. So the coupling between the density and the magnetic field can be also indicated by the density spectra that I showed in the first part. If it's homograph density spectrum, it indicates a good coupling between magnetic field, density, and also velocity. Okay, and shallow density spectrum means poor coupling. Okay, so a very brief summary of my talk. Thank you very much.
The other thing that can affect the cold density structures would be gravity. So we showed numerically with David and observationally with Nick Pingle, who was also a student at Wisconsin, that you can have in either very cold H1 or in dust a slope that's even shallower than you would predict from supersonic turbulence due to gravitational contraction. Is that something you've also considered in your numerical experiments, or?
Not yet. I mean, we were just focus on more diffuse medium, especially in this work. Yeah.
The other point is that I didn't quite catch it, but for the case with strong magnetic field, for the subsonic case, so Jagdish Kowal and I showed like 10 years ago that you do actually see an effect on the power spectral slope in the subsonic case. Is that consistent with what you were showing, or were you talking about in the supersonic case, the magnetic field, the magnetic pressure doesn't affect the slope, but in the subsonic case, we showed that it does.
Oh, okay. So here we didn't really look at the effect of the magnetic field strength on the structure. We are mostly looking at the sonic Mach number. So what's the difference on the density fluctuations?
New technology. Okay. So previously, Xiao, you mentioned in talk that in supersonic turbulence you have shock, so you have a steeper spectrum. So previously you discussed with me and Zhanfu a few months ago that you insist that in supersonic turbulence you have a steeper spectrum. But while we are showing to you in numerical simulations that in high sonic Mach number cases the spectrum is flattened. What makes you change your idea from high sonic Mach number with a steeper spectrum to a high sonic Mach for a shallower spectrum in your talk now?
Oh, I don't think I changed my idea. And if you talk about steep spectrum, I think it's velocity spectrum. But here I only talk about density spectrum, and they can be quite different in, especially in supersonic turbulence.